want to talk about dark matter, but where do I even start? I mean, it's common knowledge at this point that dark matter is the matter we can't see and doesn't behave like ordinary matter. On top of that, we have no idea what it is, and it makes up 80% of the matter in the universe. But before I get too ahead of myself, I should start with defining ordinary matter as a class. I can start by talking about how matter is defined as anything that has mass and volume, aka anything that takes up physical space. I can then go into the definition of ordinary matter, which according to Wikipedia is matter that is made up of what atoms and molecules are made of, meaning anything made of positively charged protons, neutral neutrons, and negatively charged electrons. I can then quickly mention that protons, neutrons, and other particles are made up of these heavy subatomic particles called baryons. This will be important later. I can then talk about what baryons are made of. No. That's another fish I'll fry another time. My point should be that ordinary matter makes up everything we can directly observe. We can observe it via visible light with our eyes, or we can use telescopes to direct their production of other kinds of non-visible light, such as ultraviolet or infrared. I can then go into using a bunch of examples that the viewer might know of that are examples of ordinary matter, such as themselves, phones, paper, water, earth, fire, air. All of that is made of ordinary matter, and all of that only makes up 5% of what is in the universe. The rest of it is the dark universe. AKA, we can't see or detect 95% of what our universe is made of. Way to bury the lead, Maytal. So now that I've defined ordinary matter, it begs the question, if we can't see or detect it, how do we know it's there? And for that, I should first talk about gravity. Well, we all know at this point that gravity is a force that acts on all matter, and that all matter in the universe has some amount of gravitational effect on all the other matter in the universe. The amount of gravity an object has depends on the object's mass. I should also talk about how, when it comes to the amount of gravitational force two objects put on one another, it depends on the mass of both objects and the distance between those two objects. Another cool thing that gravity can do that I should definitely talk about is its ability to bend light. I can use the example of black holes, which are so gravitationally strong that the light surrounding a black hole that isn't pulled in by it curves around it like a funhouse mirror. And if I'm talking about black holes bending light, I have to talk about how it can also produce multiple images for one object. We can see two images of the same star on opposite sides of the black hole because the light rays passing the black hole on either side get bent towards it. This process is called gravitational lensing. I should make sure to mention that this effect only is really observed with supermassive objects with a lot of gravitational influence. Now that I've provided the background information, I can get into how we figured this all out. I think I should start 80 years ago, in the year 1933, when the concept of dark matter was first inferred by the Swiss-American astronomer Fritz Zwicky, a noted curmudgeon and self-proclaimed lone wolf who claimed that all astronomers are spherical bastards. He observed that there wasn't enough ordinary matter in the Coma cluster to be holding the galaxies in it together, but he knew something had to be there keeping them gravitationally bound, an unseen matter of some kind. Then I can fast forward about another 40 years, give or take, to the 1970s, when Vera Rubin, an inspiration to all future women in astronomy and a well-respected individual by the public at the time, found the same problem in individual spiral galaxies. The stars at the edge of the galaxies were moving too fast for all of the observable matter in that galaxy to be able to keep it bound. She figured there had to be significantly more matter that we were not observing, keeping the stars bound to the galaxies. Now that the history lesson is out of the way, I can then start talking about the good stuff. What evidence we have of dark matter's existence. I should start with the biggest one, which is dark matter's gravitational effect on ordinary matter in the universe. Because dark matter doesn't absorb or reflect light, the only thing we have to work with is its mass. This is where gravitational lensing comes into play. The light from large and distant objects, such as galaxy clusters, is sometimes warped by dark matter before it gets to our eyes. We can then use mathematical models to predict the locations of the cluster and the dark matter that lensed it, as well as the amount of dark matter in that particular clump. Then I can talk about the cosmic microwave background, also known as the CMB. The CMB is the faint glow of radiation left over from the Big Bang. The patterns in the CMB can be used to infer the presence and properties of dark matter. For example, the density fluctuations seen in the CMB are consistent with the idea that dark matter played a crucial role in the growth of cosmic structures. I should also talk about the bullet cluster observation. The bullet cluster is composed of two clusters of galaxies that collided and moved past each other. Observations across different parts of the electromagnetic spectrum of the bullet cluster revealed the first strong observational evidence of some of dark matter's most well-known properties. The picture I'll use will show the red and pink hues as being ordinary matter, for example, all the galaxies, stars, and cosmic gas, and the blue and purple hues are all dark matter. I should make sure to highlight the formation that each blob of matter takes, as that will be explained a bit deeper later on. I should also talk about how we use particle physics to aid in our search for hypothetical dark matter particles. These experiments aim to identify particles that could make up dark matter and determine their properties. Finally, I can explain how, due to recent technological advances, we can now use computers to run numerical simulations of the evolution of the universe based on different assumptions about the nature of dark matter. By comparing the results of these simulations with observations of the actual universe, researchers can refine their understanding of the properties of dark matter, such as whether the particles are heavy and slow or light and fast. Okay, not bad. Where do I go from here? How about I talk about what makes dark matter so different from ordinary matter, its properties and behaviors? In this section, I'll start by clarifying a key point. Dark matter remains undetectable through direct means because it neither absorbs, emits, nor reflects light. This immunity to the electromagnetic radiation prevents its observation both visually and using telescopes or other tools surveying the non-visible parts of the electromagnetic spectrum. A vital aspect of the universe's structure involves the cosmic web, an intricate network of filaments containing all the matter in the universe. Dark matter constitutes 5/6 of the cosmic web, with the remaining 1/6 being ordinary matter. I should also be sure to mention that dark matter isn't uniformly distributed. It forms clumps of varying sizes within the web. These variations are observable by studying the bending of light from distant objects, reflecting the strength of the gravity and indicating the presence of more dark matter. The interconnected clumps resemble the neural pathways in a brain when mapped out. In the collision of two galaxy clusters, stars rarely collide, while gas and plasma interact through gravitational and friction-like forces. Dark matter, expected to be collision-free, passes through at high speeds unimpeded. In the collision, the high-temperature gas within each cluster experiences deceleration and deformation due to a drag force akin to air resistance. In contrast, dark matter remains unaffected by the impact, since it lacks direct interactions with itself or the gas, except through gravity, leading to its separation from normal matter. Larger dark matter clumps exert gravitational influence, pulling in more ordinary matter. These clumps play a key role in shaping galaxies and galaxy clusters, contributing significantly to the overall structure of large cosmic objects. I can then talk about how dark matter is thought to be stable and long-lived. To drive the formation of large cosmic structures, especially in the early universe, the presence of dark matter was essential. Without it, the early universe lacked realistic conditions for such structures to form. Dark matter's apparent lack of annihilation or interaction over the vast expanse of the universe's existence suggests its remarkable stability and longevity. Then I can go into dark matter falling under what physicists call non-baryonic matter. As I mentioned previously, ordinary matter is made up of what we call baryons. So, non-baryonic matter refers to the matter that is not made up of the stuff ordinary matter is made of. This is matter that is not made of our usual protons and neutrons. I can then start getting a little bit more into the theoretical side of things. The current leading theory is that dark matter is made up of particles that move slowly compared to light, and only rarely interact with each other gravitationally. This is known as the cold dark matter, or CDM theory. Finally, I can go into some previously shut down theories about what dark matter is. Dark matter can't be diffuse hot gas because it would produce X-rays, but it doesn't. It can't be small lumps or snowballs of hydrogen because then it would evaporate, and as we know, dark matter is very long-lived. It can't be cool neutral hydrogen because we would see it in quasar absorption lines, but we don't. And it can't be rocks or dust because it would have a high metallicity that we would be able to detect. Next, I could talk about some more recent and up-to-date theories about what dark matter is. Particle physicists propose various models for dark matter particles based on their understanding of fundamental particles and forces. Observations hint at the existence of an unidentified type of particle constituting dark matter. One proposed category includes particles which emit gamma rays or X-rays upon decay. Researchers are actively seeking these gamma rays/X-rays in regions rich in dark matter but lacking gas, such as colliding galaxy clusters where gas has been displaced. These models can help predict the behavior and properties of dark matter particles, such as their mass and interaction strength. One of these proposed models is weakly interactive massive particles, more commonly known as WIMPs. The biggest thing I should mention about WIMPs are that they are, as the name suggests, massive particles, weighing anywhere between 1 to 10,000 gigaelectron volts. For comparison, a proton or neutron is only 0.983 gigaelectron volts at most. They also don't absorb, emit, or reflect light. They also don't interact strongly with other ordinary particles. However, they do interact with each other. When two WIMPs come into contact, they annihilate each other and emit gamma rays in the process. WIMPs are a favorite candidate of astrophysicists for a couple reasons. For one, they can calculate how many there likely are in the universe. Because WIMPs are their own antipartners, their annihilation rate in the early universe can be estimated and used to determine their abundance today. They are also a favored hypothesis because they already exist in our current understanding of particle theory in something called supersymmetry, also called SUSY. The theory of SUSY, without getting too into the weeds of particle physics, states that for every elementary particle we know about, there is a supersymmetric particle, or superpartner, for it. The heavier superpartners decay into the lighter ones, eventually leaving us with the lightest supersymmetric particle, WIMPs, which could be dark matter. However, after recent studies using telescopes meant to detect gamma rays found no such gamma ray bursts in regions of the universe with a lot of dark matter, the theory of WIMPs was since put on hold. I can also talk about the other side of that spectrum, a possible particle known as axions, which emit X-rays upon decay. They don't interact with any elementary particles in the Standard Model. They are theorized to have no electric charge and a very small mass in the range from 1 microelectron volt to 1 electron volt. They also have a very low likelihood of interacting with any other particles, both with itself and with ordinary matter. Axions make for good candidates for a few main reasons, all based on current theoretical models of axions. They are suggested to be very stable and long-lived, which, as was mentioned earlier, is consistent with the properties of dark matter. The abundance of axions in the early universe could match the observed abundance of dark matter in the early universe. If axions are dark matter particles, they could provide one solution to two of the biggest questions in both cosmology and particle physics. Axions arise from theoretical extensions of the standard model of particle physics, particularly in the context of solving the strong CP problem. The strong CP problem is a puzzle posed in particle physics related to what happens to particles when they are switched with their superpartner or when they are flipped around like a mirror. Axions provide a theoretical solution to this problem and simultaneously offer a candidate for dark matter particles. However, in analyzing X-ray emissions in areas with an abundance of dark matter, a similar fate befell the axion hypothesis when no notable X-ray emissions were detected. Finally, I can briefly talk about the craziest idea out there. There is no dark matter. Instead, our theory of gravity is wrong. This crazy idea was first proposed in 1982 and heavily altered from then on. The idea is called MOND, or Modified Newtonian Dynamics. The current idea of MOND essentially adds two extra gravitational fields to our current universe. So instead of our universe just having a vector gravitational field, it was proposed that there was also a tensor gravitational field, which is just a multi-dimensional array, and a scalar gravitational field. Thus, TeVes was born. But even still, TeVes crumbled when matter was introduced. Since then, some cosmologists have been working to try and make this TeVes and MOND idea work. At this point, there is no right answer. If I'm being completely honest, I'm not super convinced. They started with equations and then shoved previously unimagined parameters to make the existence of dark matter obsolete, and it still left them with extra unaccounted for mass. It just screams, "You're probably wrong, but I love the enthusiasm," you know? Regardless, there's no doubt that if this hypothesis turned out to be true, everything would change. Okay, I'm done with my outline. Time to get to filming.